Okay, who's ready for our next chromatography concept? I know that I am, and I hope that you're ready, Freddy. So we need to talk about partition coefficient. All right, so partition coefficient. Now, what I'm getting ready to explain is basically a concept that we really don't do anything with in this format, but we do change it a little bit, and we look at partition coefficient in a different way more commonly. All right? So here's what you've got to think about with partition coefficient. First off, I've got my column, right? And in the column, I have my stationary phase. And through the top, I am putting my mobile phase through the column. And my component is on the inside. And I'm just going to draw my component as a purple little dot. Okay? So what you got to keep in mind is that this component is going to hang out with the little stationary phase particle. And then it's going to hang out with the mobile phase. And then it will hang out with stationary phase. Then mobile phase. Then stationary phase. Then mobile phase, and it can't really make up its mind. It's confused. And you've got to help it be not confused. And that's what partition coefficient is all about. Okay? So it basically takes a look at the concentration of your component in the mobile phase, and it looks at the concentration of the component in the stationary phase. And it takes those two concentrations, basically like equilibria that you learned about in maybe a second semester general chemistry class, right? Your K equilibria expressions. K equals product over reactant. Well, we do the same thing here. K is equal to, but in this case, instead of product, we're using the concentration in the stationary phase divided by the concentration in the mobile phase. So it just basically gives us an idea of how much the component likes the stationary phase. That's what this thing is all about, right? Does it prefer the stationary phase? If so, it's going to move in for a while. I hope that you've got enough food for it. Or does it not like the stationary phase? And it's just one of these users as your friends that come and go as they please until something else better comes off maybe a couple of days later down the road. That's what partition coefficient is all about. It's like an equilibrium constant. And it gives us some information about how preferred the stationary phase is to it. Okay, so that's what we call partition coefficient. We're going to kind of leave this concept as it is right now, and we'll come back to this a little bit later on. As far as equations go, you're probably never going to see an equation that uses partition coefficient. How are you going to calculate the concentration in the stationary phase and the concentration at the mobile phase at any point in time very easily? You just can't do that. So theory-wise, be prepared to explain it. Be prepared to maybe write one or two sentences on what partition coefficient means. But as far as solving an actual equation, then we're going to hold off on that and say, nope, not really. Okay? All right. So the next concept that we want to talk about is something called retention factor. And retention factor is not retention time, okay? Retention time is different than retention factor. I'm going to say that again because this is what people get confused very often. Retention factor is not the same as retention time. Sometimes retention factor is called capacity factor. And the reason for that is so it doesn't get confused with the word retention. So this was our way of maybe trying to alleviate some of those problems and some of that confusion that would happen in a laboratory. But the retention basically is not the retention time that we've been talking about up until this point. Now, it does have something to do with retention times. We use retention times in the equation, but that's how this word retention factor came along. But the problem is that people were getting it confused with the same thing, and it's not. So how do I calculate capacity factor? Well, first, capacity factor is going to be abbreviated with a very tiny k, so a little bitty k in this case. And we're going to write a big A here. So K prime A equals T sub R prime divided by T sub M. And these values you've seen before. In a previous video, we've talked about them already. So this is just another way to describe the migration rate. That's all that this basically is telling us. So this equation, the reason I'm following it up from partition coefficient, is because this equation is derived from the partition coefficient from up above. So if you look at the big K and the little k, and you look at a numerator and a denominator, the template of that equation is very similar, but they are a little bit different. So we still talk about the mass in the stationary phase and the mass in the mobile phase, and we relate that to time instead of concentration. And that's what we call capacity factor or retention factor. Okay, so basically this is the adjusted retention time that we've talked about before. We know how to calculate the adjusted retention time, and then we divide it by the dead time, or the time that the mobile phase takes in the column itself, and we get an answer. The answer is going to be maybe a range. And over here to the side, I'm going to kind of write a cutoff value for you. If the capacity factor, K prime A, is less than 1, then that means that this run, this analysis that we're doing in chromatography is way too fast. It's not spending enough time in the stationary phase. We need to give it more time to hang out before it makes the decision to go on through. So that's the purpose of the capacity factor or retention factor number. If this number is greater than 20, then that means that this thing is way too slow. It's spending way too much time in the stationary phase. It's staying so long that it's not welcomed there anymore, and it needs to be kicked to the curb. And this means that we are spending too long on the analysis in the chromatography system. So what's the kind of Goldilocks number that we want here? What we want to see is a value that's between 1 and 5. If we see a value between 1 and 5, then we're good to go. That means that the stationary phase is holding it back a little bit. It's taking its time and it's not rushing through. Separation is probably happening like it should be before it comes out of the column. And I can feel pretty good about these numbers. So if I can take a component, right? We're talking about a component on a chromatogram here. If I can take a component, and if I know the retention time of that component, and I can calculate the adjusted retention time, and I know the mobile phase time, I can take those two numbers and divide them to see if my component is actually spending enough time in the column before it comes out on the other end. And 1 to 5 is going to tell me that answer. If I get a number greater than 5, it's okay. If I get a 10 or a 15, it's okay. But once I reach the 20 mark, I really have to consider, what the heck am I doing in this lab? Because I'm wasting my time, and I'm wasting the company's time, and I'm wasting money, and I need to provide a better method analysis than this. So that's an equation that we can use to kind of judge that system whenever it begins to happen. So that's the story with partition coefficient, and that's the story with retention / capacity factors. This equation you will use on a test. That equation you will use in the laboratory. The one up here for partition, not so much. This is just basically a way for us to describe what's kind of happening on the inside.